So that gets us into describing the two main types of spectroscopy, the Fourier transform technique and the dispersion technique. So what I've been describing up to now is the dispersion technique, right? Typically UV vis. Okay? So in dispersion spectroscopy, it's the measurement of the absorption of light of a single or narrow range of wavelengths one at a time. So these wavelengths are typically scanned one at a time using a diffraction grating, right? So we would have our diffraction grating right here. We would have our incident light coming in, and let's draw a couple of different colors right here. Okay. And we would have our sample perhaps somewhere right here. And we would actually rotate that monochromometer, one angle or one wavelength at a time, whatever our resolution is capable of doing. Okay, where our detector is now going to be on the other side of the sample, right? And so we would do that one at a time, and our spectrum would be put together by scanning through all of those wavelengths. Okay, so again, that is pretty much UV vis. UV vis is pretty much exclusively dispersion spectroscopy, and that is typically done because these diffraction gratings can be made quite small, and we can just use a regular ordinary white light source. So it really is a matter of convenience based on the wavelengths that we're using. So for example, if we wanted to use dispersion spectroscopy for FTIR, we could do it, or for infrared rather. So we'll say visible, ultraviolet visible. We could absolutely do dispersion spectroscopy with an IR source of light. It was done before the FTIR existed. However, that is not convenient at all because of the size of the wavelengths. Remember, IR wavelengths are much bigger. The grating would have to be huge. It would have to be so huge that you couldn't conveniently use the spectrometer on a bench top. I mean, these gratings would have to be approaching several meters in size to use, FTIR or NMR, particularly if we wanted to use a dispersion or a grating for the radio waves associated with NMR. They'd have to be several meters in length. IR, perhaps, several dozen centimeters in length for the grating. It can be done, but it's not very convenient. So the Fourier transform technique, so Fourier transform is a mathematical algorithm. Okay, so we'll write that down. Mathematical, assuming I can spell algorithm. I probably didn't spell that right, but that's okay. So it's a mathematical algorithm that converts the time domain to a frequency domain. And that's convenient. And by domain, I'm talking about my range of values. And so that's convenient because if we think about things in terms of frequency, we can easily convert that frequency into a wavelength, which is what we're interested in spectroscopy. Okay? So in the FT technique, all of the wavelengths are measured simultaneously at very high spectral resolution. And what I mean by spectral resolution is the difference in wavelength that we can measure. Okay? So in this dispersion technique, if my resolution, if let's say my delta lambda were equal to 1 nanometer, then that means each time I pitch that grating, I'm capable of resolving 1 nanometer from the next. So for example, I could see a 532 nanometer photon. Then I could see a 533 nanometer photon. Then I could see a 534. Well, as it turns out, that 1 nanometer, which might sound small at first, is actually humongous, because that 1 nanometer in terms of vibrations or rotations is humongous. It's way too big to be useful for the very small energy spacings between levels that we need for the infrared or even the microwave technique or even the NMR technique. All of those techniques have insanely small energy level spacings. So we have to have a very specialized way of having high spectral resolution, okay? And so we do that by using this Fourier transform. And also there's a special instrument we have to use the Fourier transform, which is called the Michelson interferometer.